So good afternoon, ladies and gentlemen. Warm welcome on this Thursday. On behalf of Francesco Pignatelli, ELISE Action Leader and Senior Program Manager, on behalf of Lorena Hernandez, Project Officer, and on my behalf, Simon Vrečar, External Consultant, all of us actually working for Joint Research Center of the European Commission. And we'll be hosting this webinar today with the title Geospatially Enabled Modeling, Simulation and Prediction. Before we start with the topic, maybe just allow me a few words about ELISE that you can see on the next slide. So ELISE is an action within the ISA Square program, stands for European Location Interoperability Solutions for e-Government. And it's one of the 54 actions of this European interoperability program that is actually tackling cross-border and cross-sector interoperability solutions for public administrations, business and citizens. And ELISE is actually one of the actions, only one action that is focusing on the location dimension. As you can see on the next slide, this webinar today is actually one of the series of the webinar series where running under the ELISE knowledge transfer activities, which purpose is actually to engage in an agile way with different topics which are relevant to the digital transformation, of course, by harnessing the use of the spatial data and technologies. And one of the aims of that webinars is sometimes also to share the results of the ELISE activities. So more information about that you can find at our Join Up ISA on ISA Square ELISE collection that you will be invited during the webinar also to visit. So let's come into the next slide, please. Today we are talking about the geospatial enabled modeling, simulation and prediction. So some of you may also remember that earlier in last year and early autumn, we held a webinar with the title actually Monitoring and Understanding Emerging Geospatial Technologies, in which there was a discussion how different emerging technology influence the development of geospatial technologies and vice versa. And one of the, let's say, of the surveys we made during the webinar turned out that actually participants wanted to hear in one of our next webinars more on geospatially enabled modeling, simulation and prediction. So that is actually also one of the purposes we have this webinar. And as you can see on the next slide, we will have a speaker here today, Danny Vandenbroucke from KU Leuven, and one guest speaker, Chris Little from the UK Met Office, that will guide us through different topics. As on the next slide, you can see that those topics would be actually describing what do we mean, what do we understand under the modeling, simulation, and prediction. So providing us some definitions, explore a little bit a history about modeling using geospatial data and technologies with some examples of how geospatial technology has been used in the past. So also in the different policy context. We'd like to zoom to the two, let's say, examples of the agent-based modeling, one of the field weather forecasting, the other one of the traffic management. So the speakers would also touch some interoperability challenges that are related to the modeling, simulation and predicting. So in particular, from the perspective of the OGC, Open Geospatial Consortium, and of course discuss a bit what the future may bring regarding modeling, simulation and prediction. Of course, at the end, there will be some time for some discussion, questions and answers. So once again, you are invited to, during the presentation, to post your comments and questions in the chat box. So Danny, I think floor is yours. So please continue.
Do you hear me? It seems I can't start my video, but okay, without video is also fine. Welcome from my side as well. Before I start really on the content, I will start with some key messages that we want to give in this webinar. There are three, in fact. Modeling, simulation, and prediction, these are not really new areas for our geospatial field. In fact, geographic information systems have always been used and relatively advanced technology to model and to simulate, to analyze. But of course, we have recent new developments that put on the table new challenges and also new opportunities. But let's say it's not entirely new. Secondly, it's also clear that you can apply modeling, simulation, and prediction techniques in many sectors. And in some sectors, they are quite advanced, have a long history, or very advanced models. And especially also with regard to the integration of models, simulations, and prediction techniques and the combination of those. A third key message from this webinar is that we think also that these new developments and in general modeling, simulation and prediction require also specific efforts for reaching interoperability. It's going beyond the traditional spatial data infrastructures where we have a lot of standardization, but also in this particular subfield, we need to do that. It's clear that recently we have seen many applications, many examples where modeling, simulation, and predictive techniques are used. Of course, in the traditional, between brackets, fields like weather forecasting, climate change monitoring, but also in areas such as transport and mobility. Recently, these techniques also have been applied in some of the member states to monitor COVID-19, how the outbreak is happening, but also in more traditional fields like water management, forest management, in the military, security, and disaster management. So you have, it's very broad. There are many sectors where these techniques are applicable and already being applied. First, we might look into some definitions. I first want to show again a slide that was also shown at several occasions in other webinars of ELISE, where you have this tech trends watch, this mind map of the OGC, which dates from 2020. There is an update already available, I think, where you see that modeling and prediction, including also analysis, is one of the key areas where the OGC community is thinking many new developments will take place, and they want to have a look into what that would mean for interoperability challenges and for standardization. And more recently, they have a separate focus also on simulation that is more and more linked now to gaming techniques. Of course, we will not be able to dig very deep in a 45-minute webinar, but at least we want to provide an overview, mainly also with some examples. But before doing that, I want to provide a few insights in what do we speak about? What are the definitions of modeling, simulation, and prediction? Modeling and simulation are often going together in the sense that the simulation needs always a good model of the Earth, of the real world. And the modeling, of course, in the traditional geospatial field has been done all the time for years and years. And this is a basis, but it's going beyond that, because some of the events, the natural events, and what is happening in reality are modeled also through very dedicated and specific models that do something with geospatial and other data to simulate a state of, for example, the environment. If we speak about prediction, then we need more the element of interaction with agents, but also maybe with other things that happen in reality, in nature. So modeling, you always need as a starting point. Simulation, then simulate, like, for example, the typical example is the simulator for pilots that really constructs a reality without going in the place itself. But that's also used by the military, for example. So that is based on this model, while in simulation and prediction, you will analyze phenomena, events, and how that might evolve over time and might have another status in the future. So let's say the prediction is more to see in a crystal ball, although we all know that it's very difficult looking into the future, predicting the future, but at least in different areas, these efforts are being made. Let's say that modeling, simulation, and prediction, and often also you hear the term forecasting, they are closely related, and in a certain sense also partially overlapping. While modeling is more related to abstract or mathematical models, simulations are imitations of a situation or a process, also relying on the models, but they imitate or simulate a state of affairs. On the other hand, prediction and forecasting, prediction is the action of predicting something in the future. Can be a future state, a future behavior of people, for example. And forecasting is also a form of prediction to estimate a future event or trend. For example, if we speak about the weather forecasting, it's rather of a trend of temperature or the risk of rainfall, etc. There have been many efforts to combine different data sources from the physical surroundings, meteo data, to do some simulations and then to present it, for example, to visualize it as in a location environment in the form of a map or whatever. That has been done in the past often and is still being done by GI experts and other people alike. Without going into the details, modeling, simulation, and prediction can also have various perspectives. We speak usually of what is called the Lagrange function and the Eulerian function, or the Eulerian trail or path, where the Lagrangian function is a quantity that characterizes a state of a physical system. And the Eulerian trail or path is rather the dynamics. It's kind of finite graph, so you can visit different steps or stages in the development of something. So that's more dynamic, and also means that you might also even revisit certain points in the network. So the question is, for these two perspectives, these different type of functions that usually are used in the modeling, whether you move through the model or if you are part of the model. And at the right side, I've given an example of the intelligent transport systems, where a car system with its sensor might be able to recognize the details of the environmental surroundings, a very precise data model, a precise map, for example, including the car lanes, etc., but also other devices. While in the more advanced mechanisms and system, these cars will also communicate with each other, moving objects, but also might communicate with other sensors, for example, in buildings, an entrance of a garage, for example, etc. So, and in that sense, when exchange of information is happening through these sensors, then cars might need, especially in autonomous vehicles, to make decisions to change roads or to turn to the right or to the left or whatever needs to be done to take the next action. And that shows that already in intelligent transport system, autonomous vehicles, this has been used and is being used. So far for the definitions, I know we can discuss a long time about different versions of definitions, but that's not the aim of the seminar. I will first zoom in a little bit to explain, in fact, that modeling, simulation, and prediction, it's not new to the GI world. In fact, modeling, simulation, and prediction is in a certain sense part of what geographic information systems have always aimed to do. GIS is, of course, to gather geospatial data, to manage data. If we speak about INSPIRE and spatial data infrastructures, you set up these infrastructures to share the data, to communicate the data, or to share the data with other peers, etc. But in fact, the real original GI technology was mainly used for also analyzing, processing the data, understanding the data, combining data. And in fact, GI has always been rooted in science of geography and related sciences, always wanted to integrate different data, different layers in the typical way a GI is doing this, visualize combinations and processing of the data and using it as a map or a 3D scene, etc. So that's a unique capability. In this sense, GI technology already for a long time is quite advanced. And has been also used in many cases, in many contexts, to discover patterns, relationships, understand situations, and to take, based on that, better decisions. But since since many years, this is available and happening already. Let alone think about flood modeling. I will give a few example maps on that. Traffic modeling, it's not new. But what was happening in the past is that GI technology was quite independent from the real models themselves. If, for example, we speak about flood modeling, the Hydrological Institute from Denmark has developed the Mike Shee model, which is very advanced for flood modeling, but it's a model, a box, a toolbox that you can use to do the modeling, and then you might use the results in a GI environment or in a GIS desktop. And of course, over time, these worlds have come together more and more and merged. So for example, in some GIS packages, you have modeling capabilities, etc. But originally, they were quite separate or apart, two different worlds. To just give one example of work that already started more than 20 years ago in Belgium is the modeling of flood risk, areas at risk. And this is based on a combination of many data. We call it natural flood areas that are in fact to be derived from soil maps or can be derived from soil maps. Recently flooded data and areas that usually are nowadays mapped with the use of UAVs. The modeled areas are the ones that really rely on these flood models, and you have many tools for doing that. And you can then use also the results, of course, in the GI environment. And then you have the buffer areas, we call them, areas that we give up for water, which is a rather political decision together with citizens, where you eventually put buffers in order to decrease the risk. This is an example that you see of the Geoportal of the Flemish region in Belgium. So this result of this modeling can be found there. It's described, and every 3 years, 2 or 3 years, there's a new version, because the engineering and the intervention of human beings makes that you have to revise the modeling. But it's presented as a steady, as a rather static layer within the spatial data infrastructure, and you can use it in your GIS system. Of course, this type of approaches have advantages, but also some limitations. So when the GI environment and the models are separate, you might have GIS layers and other data that you can combine. Usually, you use also some of these data as input to the model, but output will then go back to the GIS. You need to regularly run your model with new data because of human intervention, but also the metadata you require in these models. Everything is changing all the time. So, but you might engineering interventions as well. And of course, what we see also in the application of this modeling is that sometimes it's done in a very simple way. For example, in the case of flooding, only relying on a digital terrain model or mainly relying on that. In more complex ones, you integrate hydrology and hydraulics, and I will come back to that because in the meantime, there are also dedicated standards environments for doing so, because the hydrology and the hydraulics world are two different worlds also. If you put it in a kind of architecture figure, and then we come to section 3, is that let's say that the GIS world was always there, where you have source data, you can do things, but you had a lot of, let's say, between brackets, manual interventions, and then you had some computing times. But if we shift gradually to the modeling and this, the simulation world, then take over by the machines, and the power of the machines becomes more important because we do more processing. We have more complex algorithms, etc. And the manual part is decreasing or less important. But at the end of the day, especially those traditional models as they exist already for tens of years, will generate new information layers that you can visualize, that you can use for policymaking and decision making. So with the example on the flooding, I hope I provided you an example of advanced modeling that already exists for some time. Now we want to zoom in on 2 examples, and I hope that my colleague Chris Little is in the room in the meantime, because we want to start with the example of weather forecasting. Chris, are you there?
Can you hear?
Yeah.
Can you hear me?
Yes, I can hear you.
Right. Okay, I can't see anything. But because I can't get into the system, because our system does not allow me to use Zoom except from a browser, and EU doesn't allow access via a browser. Right. So
okay, I am. If you have the slides before you,
I have the slides.
I'm on example 1, weather forecasting with the example of windy.com.
Yes. Okay. Right. Weather forecasting. Right. I've got less than 15 minutes. Weather forecasting has been around for 2,500 years. It's kind of a joke, really, from meteorologists that we all start with the earliest weather forecast, which was Noah loading animals into the ark. And the whole point of that is not that it was a very good long-range authoritative weather forecast. It was that Noah acted on it and everybody else didn't and suffered. And if you are not going to change your actions as a consequence of a forecast, you don't need a forecast. It has to be actionable, right? And that's been around for hundreds of years. And it really started in 1853 when they started standardizing data to stop ships sinking. Right, so if we move on to slide 2, which is that one.
All the formulas?
And all the weather for all the equations. Basically, meteorology was, people were forecasting before the science. That's what Fitzroy did, and he invented the word forecasting because he thought the word prediction was too precise. But it was only about 1890 when Wilhelm Bjerknes, a Norwegian mathematician, physicist, and meteorologist, wrote down these equations. And he said, these are the 5 equations, simultaneous equations in 5 unknowns that determine the motion of the atmosphere. And they weren't actually solved until about 1920. using data from the First World War by Richardson, and it took him 6 weeks to do a 6-hour forecast. That's 24 weeks, half a year, to do a 1-day forecast, and it was completely wrong. Completely wrong, and the science kind of took that step back and got it fixed in the 30s by Jules Charney, produced a new version of the equations, and then they were tested out on ENIAC by John von Neumann, one of the first digital computers. Won't go down that route of which was the first. And they did a weather forecast in about 1949, 1950. And it took them 24 hours to do a 24-hour forecast. So there was kind of progress there. And the computers have been getting faster ever since, and the weather forecasts have been getting better. And there's what's not revealed in those equations is, as you solve those equations with a higher resolution and a higher space and time resolutions, the forecast gets better. That's a sort of a consequence of the mathematics, irrespective of getting better data. You generally need about several orders of magnitude to make a step improvement, because if you increase the resolution horizontally, that's 4 times as much data horizontally. You have to increase it vertically, 8 times as much data. You have to increase it the time steps, so that's 16 times as much data. You have to then improve the physics, which is the next slide. So we've got lots of complicated interaction that are going on, and that gets more complicated. So you're really talking about at least an order of magnitude improvement requirement in computing power. But we've got Moore's law, and that's been working ever since. The data is complicated, and you can see from that graph there, that's a kind of a chart a forecaster would typically look at to figure out what's going on. And you've got observations, you've got the forecasts, you've got imagery, satellite imagery, radar imagery. It's all very complicated, and that infrastructure has been in place for 50 odd years, and the issues aren't going to go away. You need global data to do global forecasts. You can't do a local forecast unless you do a global forecast. So if we go on to the next slide, there's all this infrastructure that was set up after the Second World War, and all 193 countries have a national Met service, and there's all sorts of different services, not just weather forecasting in the simple sense, but you've got severe weather centers forecasting for hurricanes, threats to life. And here's the region on the right is who's got responsibility for forecasting tropical storms. But of course, all these centers all talk to each other, and they also talk to the other Met services. So for example, Miami, when they're forecasting hurricanes to hit America, they will routinely use the look at the forecast from the UK and from the European Weather Centre, which is in Reading, as well as Canadian forecasts and the French forecasts. So it's all very international, and it's all global infrastructure. And Ayayayoku volcano, of course, when it erupted about 10 years ago, that closed a lot of airspace, and that was an obvious impact. And again, there's volcanic centers around the world responsible for forecasting for airspaces. Now, the important thing about meteorology is there's lots of scales of motion. So that's the slide on the right. So you have a tornado, which may only be a kilometer across, or the cloud it comes out of, but you can only and it only lasts for about 10 minutes. So you may be able to forecast it 30 minutes in advance, and you need a resolution of 200 meters, which you can't do for the globe. At the other end of the scale, you've got the planetary waves, which control, whether in a northerly airstream or a southerly airstream, and they're very long-lived, and you can forecast those days in advance, weeks in advance, a week in advance, but not much more than a week in advance. And then after that, it becomes quite difficult. But you can make predictions of the smaller scales in a probabilistic sense at the long time scales. But deterministic forecasts are quite short-term. And the way we handle the probabilistic forecasts is we issue lots of them. In a sense, it's a probability distribution. I don't think I've got a slide about that. No, that's it, I think, isn't it? Whoops, slide's gone to my. Sorry, I'm just kind of figuring out what slide I'm meant to be talking to.
The one with the different levels, scale levels.
Yes, yes, that's right. So, so you can see from that that we get really reasonable forecasts for up to a week. For 2 or 3 days, very deterministic, and in fact, the rules in meteorology are usually up to, say, a 3-day forecast. You say it will rain on Sunday. But what you should say, because that's 3 days away, but for Monday, because it's more than 3 days away or 4 days away, you'd say it will probably rain on Monday. But that's kind of an arbitrary thing. But that timescale is getting longer as when you can make a good deterministic forecast. But when you're doing a probabilistic forecast, it really depends on the customer. So if we go on to the next slide, it's what the impacts are. So what I should say is, let's take an example of forecasting for concrete. Suppose you live in a house with a garden next to a big bridge that's going to be built. You in the garden are going to build a little shed to put your gardening tools in. You're going to lay a bit of concrete, about 2 meters by 3 meters. You can do it yourself, but you want to know if the temperature will fall below 4 degrees, because below 4 degrees, you can't lay concrete to get ruined by the expansion of water and ultimately frost. So I can give you a forecast for tomorrow, whether the temperature will fall below 4 degrees in your garden. Next door to your house, there's a big superhighway being built, and they're going to make a river crossing with a big suspension bridge, and it's going to cost €1 billion. You've got exactly the same problem. You're going to lay a lot of concrete, but it costs a lot of money. So I will actually not give you the same forecast. I will give you a different forecast, because your socioeconomic costs and benefits of the wrong decision are much greater. So you get a much more conservative forecast than just for laying your shed foundations. Even though it's exactly the same forecasting principle, it depends on the user. So basically, every user has to have their own tailored forecast depending on their profit and loss. And that's the state of the art of meteorology. And that's not going to change, because that's fundamental physics and mathematics. And of course, as the resolution of the models has increased, we have some fundamental problems, such as electricity. The big supercomputers take 5 megawatts of electricity. And so now we don't talk about how fast the computer is, but how much electricity it consumes. And we are now talking about putting the computer centers in Iceland, for example, where there's a lot of geothermal green energy, and it's more effective in terms of climate change and how much carbon you've got to burn to produce that electricity to do the weather forecast. So those are kind of fundamental issues that are not going to go away. And of course, the data is now very big. So there's only perhaps 20 centers in the world doing global weather forecasts. There's perhaps 70 or 80 centers now doing regional forecasts, and the remaining 100-odd countries are relying on the others for their digital weather forecast, or manual processes even in some places. So I think where we get to there is that's a lot of data. So typically a weather forecast would, you can't actually do high resolution forecast for the whole globe. The state of the art is about 7 to 10 kilometers for a global model, having data value, a grid point at every 10 kilometers across the whole globe, perhaps 100 levels in the vertical, and then you can run that out for 5 or 6 days. So that you're talking about, and you do that maybe twice or 4 times a day. So what you're talking about is terabyte of data every few hours. You can't move it. So it's got to stay where it is, and your applications have to come to the data. And that's the kind of, we'll talk about that later. And that's a fundamental problem. The data is really big, it's volatile, you can't move it around because you're constrained by the speed of light. And you need a supercomputer. You can't do it on a room full of computers because they're too far apart. To do the calculation, the speed of light is the constraining factor. If you've got 2 chips a meter apart, it's going to take 3 nanoseconds to get a bit from one to the other. That's too slow. So that's where I'm going to stop. The real issue is blending the data with the customer's data and looking at the impact. So over the last 10 years, there's been a steady change from saying, oh, we're forecasting very heavy rain or very heavy snow. When should we issue a warning? Should if the snow is going to be a meter, we'll issue a warning. No, that's not good enough, right? In Paris or in London or in Brussels, you have 2 or 3 centimeters of snow and the city grinds to a halt. If you talk to the Finns or the Canadians, they wouldn't get out of bed for any snowfall of less than a meter or even 2 meters, right? So it's actually the impact you're concerned about, not the absolute values of what you're predicting. So if there's been a lot of rain, you may only need another centimeter of rain to overtop the flood barriers. But then if it's been dry for a long time, you're not worried if there's 3, 4, 5 centimeters of rain. Yeah. So it really is the impact and the hazards. And so I'm going to stop there.
Yeah. Thank you, Chris, because you will come back or intervene at the end also when we discuss interoperability and standardization, where also relevant developments are taking place. I will give the other, zoom in on the other example, which is related to traffic management and the application of agent-based modeling. This has been a real live project, let's say, also in Belgium, where the idea was to provide a tool to provide strategic advice on urban parking planning and evaluate parking spaces and policy and do some simulations. It was a joint effort of different partners from different perspectives, with transport experts, psychologists, and geospatial experts, and that was our role. Agent-based modeling, I will come back to a definition on that, but to frame the problem, in reality, drivers, which are the agents in this case, spend a lot of time yearly, in fact, to find parking spaces. So it has a cost in time, in fuel. Some people get frustrated, really. These are some figures that you see there in the blue box from the UK. I think it's only figures for England from 2017. So also in Belgium, the idea was to improve urban parking planning. And that was done through an agent-based modeling approach, using also geospatial technology to enrich the models with agent-based information. So there is one definition here in the blue box from Diosar, who was involved in the study, who says that it is about simulation of actions and interactions of agents, autonomous individuals that behave in a network, on the street network in reality, to predict the actions that are coming and to, in fact, model complex phenomena. In reality, the study was focused on the city of Leuven as a kind of case study. It's not the biggest city, but was an interesting case. As I said before, the agent in this context is the driver, and it is about behavior of drivers. And the model that has been implemented and developed allows to be flexible and dynamic. In the context of this study, it was focusing on road traffic, so not including buses and pedestrians, etc. That could be done in the future. So it was a kind of limited setup, but quite interesting to use geospatial technology for more advanced modeling. For the simulation of the behavior and the mobility of the actors, all the information was gathered on a one-day periods, because people start in the morning to do things and then go home at evening and then go to sleep. So usually it's one-day periods. The temporal resolution was quite detailed, so gathering a lot of information through various means, not really fully automated yet, so that's another future step potentially. The spatial resolution was to look at street segment level, and then the idea was to group agents representing the driver population with different type of different type of drivers indeed. And the agent's movement was then modeled based on activity schedules. So it's kind of initial status of the agent. The network is the baseline to model everything. And then there were several time loops with a lot of information gathered from different actors and different activities they were involved in. The network was not a very simple network in the sense of the network definition, for example, of Inspire or in traditional SDIs. It was more than that, and it was processed to, in fact, to be able to host the model and to be able to apply the model on it. So it was kind of divided in cells in which the cells were fixed 7.5 meter length. We worked with single lanes because of the structure of the city of Leuven. So in two directions, one lane in each direction. There was a modeling of the crossroads against or according to the first in, first out principle. Parkings were also coupled to the cells. And then at the border of the city, you have kind of entrance, exit gates that play a key role in the handling of the traffic that were also put in the model. You see at the bottom how this works or how this is translated in graphics. And as I said, we need, of course, geospatial data, but even more important are the non-spatial data. The road network included also driving direction, speed, hierarchical systems, so major roads against minor roads, etc. And then regarding the parking lots was including the private parking spaces, on-street parking space, and of course also the big lots, the underground garages or garages in buildings. Related to the activities which were key, that was all collected in this study with local surveys that could be complemented in the future in a more automated way through, for example, collection of information through mobiles, but that was not done in this study. So the activity schedules are key. And then, of course, you have the agent population that was then put in different categories to classify, in fact, behavior. What did it mean or what was done? In fact, it was a full workflow first to start from supply and demand, supply of parking spaces, and then the demand for parking spaces that are related, of course, to certain activities. And that was the second step. All agents, drivers have a kind of activity schedule that is related to a location. One example is given in the blue box. Agent A might go to work at 8:05 to a precise position. It can be a building. For example, the map that you see on the slide indicates certain buildings of interest. It can be in the form of an address or an XY coordinate or a combination. Then the agent goes to a shop at just after work, 16:40, and then a little bit later going home to another place again. So that's what is called the agent activity schedules. And in each step, the agent will have a behavior for finding a parking space when using the car, trying or starting to search for a space. For example, there are different typologies. I'm rather the guy who will drive to a place and directly look for an underground garage, go into that underground garage, pay for it, and then walk the last 200 or 300 meters, while my wife will try to go as close as possible to the shop and if possible drive into the shop and then make turns and circles to be able to find the closest place. But of course, I will be the first if we go together and have each our behavior. So different behaviors, typologies, and then of course, a driver might have different iterations of searching because you might go to the place where you need to be and maybe you don't find anything, you make a new round, you change eventually strategy. So there are search strategies by drivers in function of utility, own preferences, and that depend on distance, time available, pricing, etc. So we involve 3 levels, the distance, timing, and pricing levels in our case, in our study. And then, in fact, each agent has this chain of activities and different steps, and you can model that. And the outcome, one example is given in the right figure, where you have patterns of shopping patterns, in fact, where people are looking for parking space to go to the shopping areas and different addresses, and you see that in the morning there's a high peak, etc. So you can model the behavior, and at the end of the day, this is further split and analyzed. And in this particular case, the results have been used to decide on optimal places for developing new parking spaces, taking into account the behavior of people on the one hand, but also maybe to implement also new pricing schemas to discourage people to drive in certain areas, but rather to push them to the outside, the outskirts of the city of Leuven, in order not to burden too much the city center. So in the future, because here the focus was on road networks and traffic with drivers in cars, but multimodal transport would be the next step, where you can combine it with pedestrian, with walking, or with other modes of transport. You can put in ecological parameters, etc. And you can go very far and also simulate, in fact, the negative impact or the improvement of the impact of less congestion when you plan your parking spaces in a better way, and you spread, for example, or you discourage people to make a lot of turns and turn in circles to find a space when going to a shop or to a school or to whatever address. Also, in the future, automatic data collection would be an idea to collect also different data streams instead of also putting information through the surveys. In this case, the psychology department from that other university was also analyzing the behavior of the drivers to see what they are doing when they start looking for the parking space, their frustrations eventually, etc. That was all recorded in this model. That's the example, the second example that we want to give. And now we tackle the last part, which will be more on the interoperability efforts and challenges related to that. This picture is not complete, but it's clear that in the Open Geospatial Consortium and in other places, there is some efforts done related to standardization and interoperability that have a direct impact on how the modeling, the simulation, and the prediction is done. You have 2 areas that are provided here in the slide. One is everything that has to do with simulation and gaming. That is now a separate sector that's very relevant for aeronautics, but also the military. So there is a defense and intelligence domain working group in the OGC, while you have also a specific working group on simulation and gaming, and a series of standards called the Common Database CDB series of standards are being developed in a standards working group. So to try to support, in fact, simulation and gaming operations and activities. In the Meteo Ocean, but also in the hydrology domain working groups, you have similar efforts to do that. And there are also some, of course, efforts done in the World Meteo Organization. And there are also particular organizations that focus on particular aspects. For example, to bring hydrology data models or modeling together with hydraulic modeling and to try to speak to each other. I think in the discussion session that Chris wants to intervene on that because he has some comments on that, how that cannot be used, but I will first finish these slides just to provide the overview. In some of the testbeds of OGC, some of these testing is brought together in some of the settings. So in testbed 16, 15, and 16, there were several activities on modeling, simulation, and prediction. Some of the OGC standards, basic standards like WCS, WPS processing services are already used in the context of modeling and simulation. And for example, this eHabitat is a project where this has been done to try to design and to compute likelihood of finding ecosystem with similar conditions. By the way, this was a project in which GRC, the Joint Research Center, was also involved. Regarding these particular efforts for standardization, so standardization and interoperability, not of the data necessarily only, but also of the models, where you have hydrographic or runoff models and the hydraulic models that includes also engineering aspects, where openmi.org has been developing some approaches and some standards that allows, in fact, the models to communicate with each other through an API. And so not only aligning or helping to exchange the data between the models, but also to let the models themselves talk with each other and the different components with each other, so that the output, from example, from a runoff model can be generate input automatically for the hydraulic model. So also following several scenarios. I will end with one other slide and then some conclusions and challenges, and then we can go to the discussion. And then I think also Chris wants to add some other ideas on how we are evolving in the current, with the new current technological trends in this whole modeling, simulation, and prediction world. An interesting initiative is the Model Web initiative from GEO and GEOS, the group on Earth observation, where, and there's a paper on that, you can see it at the right. Also GRC is involved in those developments, where the idea is also to go beyond the provision of data and to have platforms with data and information and gathering and exchanging of information towards a dynamic web of models, where you have environment, data spaces where researchers, managers, policymakers, even the general public, citizens can come together, rather to model, because that's how we think, how we act, what if scenarios, to put that on the table, to play around with the data, with the information. And the idea would be to further develop that idea so that we, on the web, we do not have only data sharing, but that we also can do more advanced work. Some of the key takeaway messages, and then we open for discussion. So it's not new. Modeling, simulation, and prediction, certainly in our domain, it's not new in the geospatial world. It's being applied in the past and also more and more now in different application domains. The list is very long, and there are new ones that are emerging, like the assessment of the spread of the COVID-19 pandemic is a typical case or a typical example. There are already some geospatial standards available or under development, and new ones are emerging. And I think Chris has there an important reference to be made of ongoing work in the discussion. Some challenges and priorities will be, of course, we referred already to it, is the huge amount of data coming from everywhere, the sensors, satellite imagery, and so on. There are new opportunities related to that, but also new challenges. So the modeling and the simulation, etc., becomes more complex. There is also the new technologies that can support the modeling and the simulation. Internet of Things, artificial intelligence techniques, sensor web, as I already mentioned, etc. And I think that idea, maybe that's a priority, the idea of dynamic web of models is an idea to be retained and to be further discussed, I think, in the geospatial community. And with that, I think I want to stop the presentation, and I hope we still have some time for questions and answers and maybe some discussions. I hand over to Simon.
Yes, thank you very much, Danny. Thank you very much, Chris. To both of you to reveal a bit of mysteries about, let's say, modeling, simulation and prediction. And I think we have already some questions from the audience in the chat. So maybe
Simon, can I just chip in there, because I've got another meeting to go to, and really I want to make my 2 points. Right, one is whether the models or the web of models or your network of models are loosely coupled or tightly coupled. If they're loosely coupled, you also limit to how much computation you can do. And the problem with meteorology is it has to be tightly coupled because you're constrained. As we say in computing, moving the data costs you, the calculations are free. And if you've got a web which may be loosely connected across the world, it takes time to get the data around, and telecoms wires still cost money. And so you have to distinguish between loosely coupled and tightly coupled, and some have to be tightly coupled because you want the results in real time or near real time. They're not all research projects. And that's the problem with the OpenMI. It's quite loosely coupled, and it works, and it doesn't work for meteorology or climatology, for example.
Mm-hmm.
Okay, thank you. Thank you very much, Chris, for sharing that with us. I hope you will still be here because there are some questions directly also to you. So therefore, since you're in the hurry, I will suggest Maggie to pose her question. So please, Maggie Hellstrom.
Yes, thanks to both speakers for a very interesting overview, very, very comprehensive and nice. My question relates to how you, what your views are on how to best, first of all, prepare, but then also communicate the uncertainties of the outcomes of these kinds of modeling activities to the different end user communities.
That's a very good question, Maggie. Hi, Maggie. The meteorologists have discussed probability forecasts for a long time. So, and you have to be very clear and very transparent and very simple about what you want to present. So if I say, for your location in Sweden, there's a 50% chance of rain this afternoon. Now, it may be that you are just upstream of a mountain and it will rain all day. So you think I'm completely wrong. You may be on the other side of the mountain and it doesn't rain at all day, and you think I'm completely wrong. But when you step back and you see half of Sweden has got rain and the other half hasn't, the user's perception versus what you've actually forecast is kind of confused. And of course, you get the same thing in time, right? So you might say there will be a thunderstorm. A thunderstorm lasts for about 20 minutes. And they're only about 1 kilometer or 2 across. So if it misses you, you think it's dry and it didn't rain. And therefore the 50% or the 20% or the 30% chance of rain you think is a bad forecast, whereas I think it's a good forecast. So I think there's a real issue there of a perception and actually being very clear about how the probability is distributed, whether it's in space or time or both. Does that answer your question? No, it doesn't. It just says it's a question. It's a real issue.
It's an issue.
Well, it's a bit like 3 men in a boat, right? I mean, exactly what you said. But the weather, I think people can, in general, just the normal man or woman in the street can sort of relate to the fact by now that it's a difficult thing to predict and etc. because they hear the meteorologists on TV talking about this. But it may be worse for these flooding predictions, for instance, or investigations, that the people might look at the map and say, oh, my house is not in a danger zone, but in fact just tweak the input variables a little bit, or you have a little bit more of rain in practice, and suddenly your cellar is full of water, and then again people will be angry or lives are lost in the worst case. So how do you actually visualize uncertainty? That's what maybe we could have a webinar just about that.
It's an interesting question indeed. I cannot on that because in Belgium I show the example of these risk flood areas which is the map that is used by the public authorities to decide on whether you get a permit to build a new house, for example. And they're very strict in that. And of course, then you might even give a permit that is just outside the area. And you indeed, as you say, in a few years, the excessive rainfall is such that also this area is flooded. Mm-hmm. But usually policymaking is taking kind of buffer. And a good example is that insurance companies are using the same, not the same map, but they use that map and they have added the uncertainty. And for example, it's put in law that they do plus X meters and minus X meter in different directions to include and to make, in fact, the area buffered and bigger than comes out from the simulations and from the model, to be on the safe, between brackets, safe side. And even that is, of course, not 100% sure. But indeed, there are also mechanisms to try to handle that in your information systems in different ways by deriving other maps that built in this kind of uncertainty and especially also in the interpretation and how the map is used by public authorities, for example. That can be done.
Yeah, but, and yeah. I can add a little bit to that because, again, flooding there are some fundamental differences that some people may not be aware of. So if you have a long, slow river, you know 3 or 4 days in advance, because there's been a storm upstream, the river will rise by 2 meters in 3 days' time. You know that from observations, from the, and long historical records. Whereas if you have a city that's in a bowl in the hills, Algiers and Athens come to mind, you get a sudden storm and the rain is all focused and the flood happens in half an hour. And you can't actually predict it on observations. You have to predict it from guessing, from a prediction, which is not the same as saying it will flood based on observations. So that's a kind of a real issue. And one of the models that is useful, that works, is aviation. Aviation is extremely safety critical, and all pilots are highly trained about what they do and what they don't do, and they stick to those rules. And if they don't stick to their rules, they stop being pilots because they can't make the slightest bit of mistake, and there's lots of margins built in. But so it is a culture that has to be built. And you see different responses in different countries to floods. So, for example, in Japan, when they have a fire in a multi-story block, a skyscraper, or you have a tsunami, the response of the population is very good because they practice it and they train for it, and it's part of their culture. The kind of things the Japanese do in response to tsunami wouldn't work in Britain because we don't have that kind of culture. We're not trained to do those kind of things. So I think it is kind of a very complex issue, and I don't think it'll go away.
No.
Okay, so thank you both for answering this question. I think it's quite, as Maggie said, we could have had another webinar dealing with uncertainties in the predicting, certainties or uncertainties in the predicting. Since we are a bit tight on time, I would suggest to move to another question. We have still two other questions here. One of them is by Uroš. Uroš, please.
Yes, can you hear me?
Yes.
Yes.
Okay, so what ABM framework software are you using in traffic management? And what's the amount of data you are dealing with typically?
Can you speak a little bit louder? You ask which software we used?
Yes, which ABM framework or software, whatever you are using, and what is the amount of data that you are dealing with?
First, maybe on the last question,
yeah.
The city of Leuven, there it was applied, is not a very big city. It's 100,000 inhabitants, more or less. Of course, it was a subset of, it was not all in the inhabitants that were involved, but a selection of a few hundred drivers were selected to test. In fact, because it was also said by Chris, this was a research setting to test the approach more than an operational setting, although it was used for taking decisions afterwards. So the data set of the network is not very complex. We speak about thousands of parking spaces, but not of millions. If you would apply it, of course, on a full region or a province or a larger area, that would require other approaches and maybe other elements. Basically, for performing the modeling itself, we have done everything in a GI environment at that time. So we don't have used a dedicated agent-based modeling software, but the whole workflow has been modeled using dedicated GI technology. But that is one of the things we might do also different in the future. I don't know if you have yourself experience in using particular software. I know there is different softwares available, but in this case we kept that quite simple.
Okay, thank you.
Okay, thank you very much, Danny.
Okay, Simon, and I was going to say Simon and Danny, I've got to go now. I'm running late for my meeting, which I'm meant to be hosting.
Thank you so much.
Thank you very much.
So, okay,
Yes.
okay.
So let's
move
to the next question posed by Gregor. Gregor, can you please put it live?
Yes. Hello, everyone.
Hello.
Can you hear me?
Yes.
Yes.
Okay, excellent. So my question is in more general, not just specific to your modeling case that you presented, but where do you see the value in preserving geospatial data for more than 10 years for future modeling applications? Because this, of course, takes some effort and some energy to do that. But if the use cases for that are there, well, I wonder what your opinion on that is.
Yeah. I think if I would refer to the one on the parking spaces, that's maybe less relevant to have historical data, although it would help, I think, if you want to make your modeling of behavior of people better, then it's always good to be able to refer or to use or reuse also historical data or bigger data sets that maybe are gathered in the context of another city or another country, so that you can also cross-check, for example, with how the behavior is there, if that would exist. I'm not aware of that. But there I could see rather limited use, but I don't know the details because I'm not a meteo expert, but I'm a geographer, so I know something about meteo, is that in the modeling for weather and the weather forecasting, they rely a lot on historical data series. Of course, you can argue that the resulting maps that provide you an overview of the weather situation in, for example, Europe or in a country at a certain point in time in the past is maybe less relevant. But the time series that are at the basis of all the modeling, they are used also for other fields such as climate change modeling. There you need more historical data or longer timelines, and also in the flood mapping and the flood modeling. For example, this relies also on historical data in the sense that the model, when you use, for example, MACSHE, is also requiring information on when a certain extreme weather event occurred over the last 50 or 100 years. So in that sense, you need this type of information as input parameters to the model. I don't know the exact parameters that this model is using, but I know that this type of information is used in order to predict, for example, the chance that a weather event that is only occurring every 50 or 100 years will occur back, and what will be then the flood risk areas if you apply, for example, the excessive rain parameters and other parameters into your model. So in that sense, yes, I think for certain cases for modeling and simulation, it's important. I think for other cases, it might be less relevant.
Yeah, and the second question is, do you think there are more cases where only local data are interesting for such models, or would we benefit from a interoperable way of preserving this type of data across the EU member states and organizations?
I think in general terms, but that's more a generic answer based on feeling, is that it would be better. Well, in the case of this parking project and the research there, it was focusing on local. But it's true that if you want, it would be better that you collect, process, represent the data in the same way if you do a similar exercise in another city in Romania or in other places in Europe, for example. In that sense, in my opinion, the way you collect and use the base data, that is of course starting point, for example, inspired data and other data, and you add and you collect additional information. There, I would say you need to try to reach interoperability by creating or trying to collect a similar data set in a similar way so that the outcomes of your exercise are comparable. In that sense, yes, that's important. And of course, if you speak about flood mapping, as an example, there it's already partially done because the experience from the Flemish region on flood modeling and also the way flood mapping is done, because it's not only the modeling part, has been retained with experience from other member states, and in fact that has been put partially in the flood directive, the European Flood Directive, to collect certain data and information in a particular way and in a harmonized way, giving some guidance on which parameters to collect, etc., etc. Because if you want to do that and approach the flood risk issue at European level, you need to do it kind of in a common way, in a common approach, and that might be common modeling models that you use, but also the data that are at the basis should be quite similar. Yeah, so in my opinion, yes, that's quite important. An important issue.
Okay, thank you.
Okay, thank you, Danny. So I see that we could have discussed quite a long on this topic. Maybe just for the end, so I become also a bit curious. So we know that artificial intelligence has actually become an area of strategic importance for European Commission, with perceiving it as a kind of a driver of all development, economic development, and tackling it from different points like technological, ethical, and so on. So how do you see those concepts of artificial intelligence and what you have presented today go along with each other in the future, and how they may mutually impact each other as well? So what's your opinion on that?
Yeah, without being an expert in artificial intelligence, far from, I know that there are some ideas to apply artificial intelligence, for example, to monitor behavior of agents. You could eventually, because not only the automation of the whole procedure is one of the ideas, and some of the other ideas I mentioned in the presentation, but for the traffic management case, I think there are so many traffic flows that, in fact, if you would analyze them by making use of artificial intelligence, you would learn a lot about the behavior of the agents, of the drivers. That's one example where I can imagine it's interesting to try to do that. I am almost sure also that it is done in intelligent transport systems. They try to do that to also keep information also from all these sensors, because you have also there massive amount of data. Like a car is nowadays a computer, in fact, collecting a lot of information, storing it. With all this information, you could do a lot, but then the amounts are so huge that it's almost impossible to do it manually. Similar things on agent-based modeling and behavior of agents has been done in other settings. Like I know, for example, also research setting where the University of Ghent has done agent-based modeling for analyzing and using, in fact, artificial intelligence techniques or machine learning techniques to understand movements of people that are going to mass events like rock concerts or other type or similar events where you have tens of thousands of people, and then analyzing based on mobile data, so from the mobile phone, how they behave, how they go from, for example, if they exit, if the rock concert is finished, how the flows are happening in reality, so how the people behave. And we have done something similar, artificial intelligence and machine learning in the context and for a project in SATSEN, where satellite imagery has been processed using machine learning techniques to try to capture behavior of human smugglers based on the recognition of certain objects in the satellite imagery, from which you also could then deduct, in fact, tracks followed by human trafficking people and organizations, for example. These are 3 examples. So I can see that these techniques can be useful to enrich your knowledge, your understanding of behavior of human beings or agents, whether that's pedestrians or cars or yeah, whatever it might be.
Okay, thank you very much. So it looks like that we will come back to these topics maybe also in the future, even maybe one of our webinars. So before we conclude, maybe if you can move to the next slide. I would like to invite you to the next webinars, or at least to the next one, which is going to be on the 4th of February. Where we are going to present the study results of the study evolution of the access to the spatial data for environmental purposes. So with this, I would like to close today's webinar and thank you all. In the first to Danny and to Chris for their very interesting presentation. And of course, to all of you that have been with us, maybe even a bit over the time. And also for posing all the questions. So stay tuned with us and we'll see you at the next webinar and have a nice day.